Hi everyone. So in this video I shall demonstrate how to design and test the design of a mixer, and this is in correlation to the course E6320 RFIC. In the previous video I discussed how to design a low noise amplifier. So in this now we shall look at the mixer design. So a mixer basically is a non-linear device that translates frequencies. That is, you take two frequencies, one probably at baseband, that is near DC, and then you do a frequency translation by a given frequency that is provided by the local oscillator, which we term LO, and change that frequency at baseband to frequency at RF. So this is a up conversion mixer because you are essentially increasing the frequency of the signal. And there could obviously be a down conversion mixer, that is, you convert the frequency at RF to baseband. That is given by the relation FRF minus FLO is equal to FBB. So both kind of mixers are possible. And in this project, we are going to design a fully differential double balanced Gilbert cell mixer, which you would have seen in the class. And the specification of this is as follows. The technology node is the same. We are using IBM 130 nanometer CMOS with VDD of 1.2 volts. And in this project, the specifications are as follows. The RF and LO frequency are from 5.17 to 5.32 gigahertz, and the bandwidth of the RF signal is 20 megahertz. That is, the baseband bandwidth is 10 megahertz. At RF, it will occupy 20 megahertz. That is, the RF frequency occupies this band, that is FLO minus 10 to FLO plus 10 megahertz. And in the simulations, we are required to set FRF equal to FLO plus 10 megahertz. Uh, and the critical specs are as follows. The conversion gain of the mixer needs to be greater than 15 dB, and the single sideband noise figure needs to be sub 10 dB. That is the integrated output noise of the mixer. And the IIP2, which is a measure of mismatch, needs to be greater than 3 dBm, 30 dBm, after applying systemic mismatch of 1% between all the devices. And the IIP3 needs to be greater than minus 5 dBm. And we need to also ensure that the input capacitance of the mixer is less than that of the LNA. If it is larger, we need to go back and tweak the parameters of the LNA at the drain end. And there is another part, that is to integrate the mixer with the LNA and determine the overall noise figure gain, IIP3, etc., and check it with hand calculation. There are no critical specs on this combined cascaded design. So now we shall look at the schematic of a Gilbert cell mixer. So this is a Gilbert cell mixer, double balanced fully differential Gilbert cell mixer. The LO input is applied here. This is the LO plus and this is the LO minus. And similarly, the RF input is also applied here. This is RF plus and RF minus. And the IF output is taken here. So now we shall look at the same in Cadence. So I have already designed the mixer. So this is the design of a mixer. This is the LO plus, LO minus, RF plus, RF minus, and this is the tail current source. This resistor is used to provide gain. This resistor is used to improve linearity. And so this is the design. And just a comment on how to draw these diagonal wires. As you might have already understood, W is the shortcut to draw a wire. So when you are drawing a wire, press W and press F3. So you can go to this mode. So in this mode, you can set the routing to whichever way you would want. So I set it to this. So in this, I can route it diagonally as I've shown here. So once you have designed your schematic of the mixer, the next step is to create its symbol. To do that, you go to create cell view. From cell view, create the symbol. I have already done that. So this is the symbol of the mixer, and this is the symbol we shall be using in our test bench. So now this is the test bench. There are two halves, one for the I part, one for the Q part, and this is the part that uh, gives the LO signals. So the settings of this port are as follows. So you set the DC voltage to 0. DC does not have any significance here. And the frequency name is set to FLO. And the 0 value is 0, 1 value is VLO, which is 1.2 volts, as we shall see. And the period of the waveform is 1 by FLO. And the rise time and fall time are both 10%, as mentioned in the help guideline. So this is the setup of the FLO port. On this side, on the Q side also, everything is the same except that we have added a delay of 1/4 to generate the VLO plus and VLO minus for the Q part. And for the basic operations such as conversion gain, noise figure, IIP3, etc., we are setting up, not IIP3, sorry, for the conversion gain and noise figure. The setup of the port is as follows. The port is set up in the DC mode, as we call, and is set to PAC magnitude 1 volt and AC magnitude 1 volt. The same thing applies for the Q port. And this RF signal is converted to its differential signal, similar to the LO, and is input to the mixer. And the other supplies are provided to the mixer, and its output is taken across this, as we saw in the case of an LNA as well. And the setup is also the same. So however, I've added a mismatch in already. It is not necessary that you already add the mismatch for noise figure, gain, etc. They will not severely attenuate your spec. So to add mismatch, the only key change that has been done is one side has been skewed deliberately. That is, the W of this is W times del, and this is just W. So each part is skewed by 1%. So that is the del factor. Uh, the other side was not skewed. And so that is set up for mismatch. And the remaining parameters are for my design. The HB setup is as follows. So I have set the frequency FLO and it's set to the center of the band, that is 5.32 gigahertz. And the HBAC is also set in such a way. And the HB noise is set in this fashion. Once the setup is done as per the help document, so you can simulate the circuit and just ensure that your model file is included. Once that is done, your circuit will run. And to plot the output, go to HBAC, select voltage, sideband DB20, and then select the output net. So this is the conversion gain that meets our spec. And this is at FLO equal to 5.32 gigahertz. For other frequencies, you will have to change FLO under rerun. So this is the conversion gain. Now to get the noise figure, also just go to the adjacent tab, that is HV noise, click on noise figure, integrate over bandwidth, start frequency from 1 kilohertz to 100 megahertz, and then plot the noise figure. So this is the integrated noise figure, that is 6.32 dB. So this also meets the specification. Now we shall look at the other analysis. Now we have already seen how to find out the conversion gain and the noise figure. Now to check IIP3, we need to change the configuration of the port. We need to change this from DC to a sine wave. So once that is done, ensure that you change the port to this configuration. You set the frequency to FRF1, keep it FRF1 Hertz, and the power amplitude in PRF. The same thing needs to be applied to the Q port as well. So once that is done, check save this schematic and relaunch ADEL. So set the analysis in this fashion. Uh, so FRF is set at 5.245 gigahertz, and this variable PRF is swept from -60 to 20 dBm in steps of 1. That is too detailed. You can keep steps of 2 or 3 also. That's okay. And so once this is done, you just need to run the HB analysis. This will take some time to run. The idea of HB is that HB is like a DC operating point for periodic sinusoidal waves that takes into account the nonlinearity as well. So HB is a very powerful analysis. We will be encountering HB many times in the future. So once this is done, so I have already set up the option to plot IIP3. So you can plot the IIP3 input referred third order interpolation. And this gives a value of -2.9. That is more than the spec. Just a comment on how to pick this IIP3. So you need to take uh, 2 FRF minus FRF, 2 times FRF1 minus FRF2 to be your third harmonic. That is here 74 megahertz. And you need to pick 1 times FRF and 0 times FRF2. That is this. You need to maintain the same FLO coefficient. So once you pick this, you can plot the IIP3. And similarly for IIP2 as well, uh, you need to change this to second order, and you need to pick as I was telling 1 times FRF1 and 1 times FRF2. How much is that? And ensure that you keep the same FLO value, that is -1. That is this frequency. So once you pick this, you can plot the IM2 as well. So I'll plot the IM2 now. So this is the IM2, and this is greater than the 30 dB specification. So this is with 1% mismatch. So it is pretty good. And ideally, in the absence of mismatch, you should expect almost near infinity IM2. However, due to practical considerations, it is not infinity, but very high value in the absence of mismatch. That is. In the presence of mismatch, it is this value. So that completes the analysis of most of the specification. Now we shall look at how to calculate the power. To calculate power in the same analysis, go to voltage and pick RMS, and you need to plot. So instead of voltage, change this to current and pick the value. It actually doesn't matter at what sweep you are looking at. So set this to spectrum, peak, so RMS and magnitude, and then you need to select the terminal. You need to select the terminal. So this is the power. The DC value is the power. So about 509 microampere is supplied. Twice of this is supplied because almost the similar current will flow through the Q branch as well. So since this is a harmonic circuit, you need to estimate power using HB and not DC. So I hope all the simulation methodologies are clear for the mixer. This is not a trivial simulation setup as in the case of an LNA. So please let me know if you have any questions. Thank you.